Alright, in this video we will discuss single loop circuits and introduce the idea of multi-loop circuits. Alright, first thing is, do you know what a single loop circuit is? So when you look at a problem like this one, right, we would assume that this is a battery symbol, and since the shorter plate is considered negative and the longer plate is considered positive, we would assume that the EMF will be pointing upwards. Alright? It looks though to me like there's two loops in the circuit, at first glance. Until we realize that both of these resistors, R1 and R2, are really just in parallel. So what we're going to do is we're going to kind of redraw this a little bit so it looks like this. And after a quick redraw, we realize this really is not a two-loop circuit if we lump these two resistors into one and call it a single resistor. So we could label this R effective. Now you cannot always do this. You cannot always take a two-loop, what appears to be a two-loop circuit, and call it a one-loop circuit. Okay, by the way, the combined resistance of R1 and R2, since they are parallel to one another, is found by reciprocal addition, right? Or the real way to say it is find the harmonic mean. So this would be the effective resistance. For example, if this was a 100 ohm resistor and this is a 200 ohm resistor, you would just basically go 1 over 100 plus 1 over 200, which combines basically to be, it comes out to 3 over 200, and then you flip it over again. So you do like 1 over that. Okay, so 200 over 3, it's a 66.6 repeating ohm resistor. So what's the difference between buying 200 and 200, two resistors at the store? One is 100 ohms and the other is 200 ohms, and putting them into a circuit in parallel, and just buying a 66 ohm resistor in the first place. Actually, there is no mathematical difference or really any physical difference, assuming the wires are negligible resistance. The only difference is you might not be able to find a 66.6 ohm resistor. You know what I mean? They might not make that resistor or sell that resistor at the store near your home. So you might need to buy a 100 or 200 and kind of just make it work. Okay. Now there are many what look like very complicated arrangements of resistors, and it turns out they can all be combined into a single one. And so what looks at first like clearly a double loop circuit is not a double loop circuit. Let me show you one more example of that. Let's say that you have your battery like this, negative, positive, so the EMF is pointing down, let's say. And then over here you have a resistor aiming diagonally, a resistor here, a resistor here. Okay, maybe in this fourth component you have the circuit branches off like this, and then back again, and then this is what appears to be a loop of its own, and then maybe even one more diagonally in here like this. Even this complicated system where you have R1 through R6, all of this can be reconfigured into a single resistor, actually. So these three on the right, I think it's pretty clear that these three are all technically in parallel with one another, right? And then you could combine those using, like 1 over R6 plus 1 over R5 plus 1 over R to the fourth. Then you flip that over. And then that resistor, which you can now just think of as one big resistor, this big thing, this big pink thing is all one big resistor, right? Think of that as in parallel with these R1, R2, and R3. So then you would just take, oops, sorry. You would take, 1 over R1 and 1 over R2 and 1 over R3, and then 1 over the pink answer you just got, right? And then you would take all that and flip it over. So it turns out actually all 6, if you think about it, all 6 of these resistors are in parallel one with another. So, okay. Sometimes they're in parallel, sometimes they're in series. Let's squeeze in one more resistor. Let's say that the original battery had its own little internal resistance. And so you could think of a tiny little R, that's internal resistance to the battery right here in the circuit. So after combining all 6 resistors into parallel form, you could then pretend that this here is a final drawing of your circuit. Watch this. So this is R effective, R combined. It's really all 6 of the original resistors combined. And then you've got this little guy right here, R, and these are in series with each other now. So you could then lump those together if you wanted to. And for these, this is in series, so you don't use any fancy addition. You just add R and R together. So the combined resistance is really just little r plus big R effective. All right, so that's the first thing. Don't be deceived by what looks like a multi-loop circuit. And if you're interested in the subject of morphing things to be shaped in a congruent fashion to before, you can study a little bit online about the subject of topology, T-O-P-O-L-O-G-Y, 3 O's there, topology. And we discussed this a bit in class. It's a fascinating topic. All right. Next. One more comment. One more thing before I do the next topic. It's important that you understand that when you go around a single loop circuit, let's say there's a couple resistors on your journey, a 100 ohm and a 200 ohm, let's say. And let's say this is your EMF. All right. Actually, let's make it general. I'm sorry. Let's make this R1 and R2. R1 and R2. Okay, yeah, that's fine. If you just think of where the positive end of the battery is, and you take a path leading from there around the circuit, right, back into the negative side of the battery. Actually, you don't want to just go into the back of the battery. You want to visualize yourself traveling even through the battery back to the exact starting location you started at. So just pick a point on here. Let's call it point A. Here's what happens when you go around like that. Okay, so you start with a potential at A. Okay, now this is some number. So it's measured in volts. It could be 5 volts. It could be 19 volts. And you might say, well, where's 0 volts? Well, we don't know. Just pretend that this is just some value, okay? As you go around this way and you pass through the R2, you're going to lose some of your potential, okay? So resistor resists high potential and drops it down. So what happens is, I don't want to put equals there. I want to pretend we're going around and we're at VA, and then we pass through this resistor, and it's going to drop by something. It turns out it's always going to drop by IR, in this case R2, because we hit resistor 2 first. All right, and then you keep going, and now we're passing through resistor 1. It's going to drop again by I1, and you get going, and then you get to the back of the battery, okay? Now at the back of the battery, if you just stop here, you haven't really gone all the way around, right? But if you keep going through the battery back to the point you started at, point A, you just went through a battery, which kind of acts like an opposite resistor. It doesn't resist anything. It pushes. In other words, it produces more potential for you. Okay, now you're right back where you started from. So basically, you started with VA, you went around, you dropped by IR2, you dropped by IR1, you hit the EMF, and it boosted you again, and now you're right back where you started from. Okay, so you'll notice something. There's a VA on both sides of the equation, and these can cancel out. Okay, so what we're saying is, if you start at a point and then you travel around through every component of the circuit and you end up back at the exact same point you started, you've experienced no potential change. There's no potential change. Which tells us something, that if you go around a loop like this, you hit every component and you adjust the potential as you go, you should get 0 in the end on the right every time. So this rule was kind of labeled as Kirchhoff's rule. All right. And what a great little tool, because we can immediately glance at a circuit, run around, and make an equation. And that's always nice. Okay, now if there's 2 loops or 3 loops, maybe you can combine them down into 1 loop first and then do the run around. If you can't seem to combine them, it could be because there's another battery in the other one of the loops. And if that happens, you might need 2 equations, 1 for each loop. But we're getting to that, so bear with me. Okay, so that's the first thing. All right, so let's go onto a similar example, this time with 2 batteries on our loop. Okay, so we have like this, maybe. Okay, this points up, and we'll call this 5 volts. And then you come over here, and then you maybe hit another battery. And this one's 6 volts, pointing to the right. And then you come over here and you hit a resistor, 100 ohms. And then you come over here and you hit a resistor, 200 ohms. All right, so let's do our little journey. You get to pick where to start, actually. I suggest we just start here, and I suggest that we go, in this problem, clockwise. All right? It's kind of up to you if you want to go clockwise or not. But I'm thinking, let's go clockwise, because I believe that's actually the way current really would go. You've got positive charge carriers here, and, you know, I drew this one backwards, sorry. This one should go short, long, short, long. There we go. I'm going to redraw that. I'm not trying to be confusing here. I'm trying to be helpful. So let me redraw this here. This is supposed to go short, long, so that the EMF points to the right. Remember, it always points short to long or negative to positive. Okay, so let's go around and let's see what we get. And then we'll also go around the other way and see what we get. So this is potential at A. So you go like this, potential at A equals, or not, I'm sorry, potential A is what we start with. And then we hit a battery first. And we're going in the same direction as the EMF arrow, so just put +5. Then we come along and we pass through this battery, so we put +6. Then we come around and we hit this resistor. Now we drop by IR, which is, I times 100. And then we keep going and we pass through the second resistor and we drop by 200. And then we're right back where we started from, so it's back to VA. Or if we cancel the VAs, we get equals 0. And so you really don't need the VA after all, do you? Okay, look at that. I think we can find the current. All right, so this is where things pay off. So you have 11 minus 300I equals 0, and then you get 300I equals 11, or you could say I is 11 over 300. And this, of course, is amperes. Pretty nice, right? Okay, now what happens if you pass through a battery that's backwards in your circuits? Let's look at that. So let's say that you're trying this problem again, but you notice something interesting. This is your 5-volt battery, but the 6-volt battery is backwards. So somebody put that 6-volt battery in backwards into the circuit. Maybe you've done that before. Maybe you've put your batteries backwards into your circuit, right? Okay. All right. So what's going on here is you have this EMF arrow pointing upwards for this battery, but on this one it's pointing leftwards. Okay, so what do I do with this? Well, let's see what happens. Let's start here at our arbitrary point A again. And we say we have a potential at A. We pass through the battery. We're going the same direction as last time. And we're passing through the battery aligned with the battery. So we're going to add 5. But when we hit this next battery, we're passing through in opposition to its EMF arrow. So we put -6. And then we pass through the resistor. So we subtract I times, I think this was 100, right? So this would be 100. Oh, Mr. Shore forgot to draw his second resistor down here, which was 200. Can you guys go ahead and add that, please? Right there. Forgot to draw that resistor. Okay. And then you pass through the second resistor, and then that's called I200. And then you're back where you started, which is VA. Cross out the VAs, as you know. Okay, now, let me change the color here. This should be a green. It's just bugging me. What happened here? Well, let's take a look at the math. 5 minus 6 is -1, and then we have that minus 300I again equals 0. This time we get that I is 1/300th of an amp. So what was it last time? I believe it was 11/300ths of an amp. In other words, this is less current. Why? Well, because some of the positive charge carriers are traveling clockwise and some are traveling anti-clockwise, which means we have sort of a net loss of current when those two batteries oppose each other. This is why many of your devices won't work if you try to put one of the batteries in backwards. It's just not enough power for that one battery to do the job alone, plus the fact that the second battery is actually opposing the first battery. So you might say, well, why doesn't my circuit like work but just not quite as well? You know what I mean? Like, how come my toy won't turn on when I put the battery in backwards? Well, if you think about it, you put in a 1.5 volt battery this way, right? And then you put in another 1.5 volt battery in this way. They basically cancel out. You don't have any voltage at all in this situation, right? Even if one of these was higher voltage than the other, and this was a 5 volt battery and this was a 1.5 volts, but sort of opposing you, you still were supposed to put in 6.5 volts into the circuit, and that would have powered the toy, let's say, but unfortunately you put a negative 1.5 here, so now you only have 3.5 volts. If the toy is going to only work when it's 6 volts or higher, putting in one battery isn't enough. That's only 5 volts. Putting in a negative 1.5 even hurts you worse. Now you're down to 3.5 volts of net EMF or electromotive force. Okay, so you're not really supposed to think of it entirely simplistically, but you can definitely see that there's less current. And it's 11 times less current. 11 times less current. Because originally this was a 5 plus 6. You know what I mean? Or, you know, it's a negative 5 plus minus 6, which is a negative 11. But now it's only a 1. So we lost 11 times our current. All right. Kind of interesting, right? Okay. Here's some things to keep in mind. If you're going to go all the way around the circuit, you're going to get a potential of 0. And if you're going to go from one point to another in a circuit, then you will not get a potential of 0, potential change of 0. All right, so let's take a look at potential between 2 points in a circuit. So let's say that you have a circuit like this. Again, we'll do our 2 resistor scenario, R1 and R2. And then here you have your battery. And I like the whole 5 volt thing, so let's go and do the 5 volts again. And let's say that you pick 2 points of interest on the circuit. So you say, I'm going to check A and B here. All right. Now, if you just travel around in the direction of the EMF arrow all the way, you're going to get 0 potential change. So, you know, the equation would look like this. VA, you'd add the 5, you'd subtract off the IR1, and you'd subtract off the IR2, and then you would get VA again because you came back to home plate. right? But if you only went partially around the circuit and you stopped when you got to point B, so let's say you just went, like this, and just stopped at B, then you would go like this, VA, add the 5, subtract the IR1, but then this is the end of your journey. This equals VB. All right, so the first one is useful, more useful, I guess you could say, because these cancel out and you get 0, and you can actually solve for I if you know the resistances. But the second one is useful sometimes because we might actually want to know the potential difference between VA and VB. Look at the second equation. You could write it like this, couldn't you? All right, so let's go ahead and put in the 100 and the 200. And let's see what this second calculation is really good for. Okay, so I'm going to erase any hint of the red arrow. We're going just the green path. And let's put in the R1 equals 100, R2 equals 200. All right. Okay. Now, you actually, when you do this little partial journey thing, you do have to also think about the full journey too. So let's do the partial and write down what we have. We'll see if we can learn anything from it. All right, let's say you have VA, you add the 5, you subtract the 100 times I, and then you get VB. Notice you never actually passed through the second resistor because you didn't do a full journey, right? Okay. Now, what can this give you? Well, it can give you VB minus VA is 5 minus 100 I. In other words, your potential will be a potential drop from 5 down to 5 minus 100I. That's one way to think of it. So if you subtract off 100 times current, that's how much voltage you're going to drop. So it's probably going to be, like 3.4 or something. Let's see what we actually get. So how do you actually calculate VA minus VB numerically? Well, you have to know I. Well, how are you going to get I? For that, you need the whole journey all the way around. So imagine going all the way around the loop. What would that equation be? Well, for that one, that would be the full journey. So it would be VA, add the 5, subtract off the 100I1, subtract off, 100I, subtract off the 200I, and then you're back to home plate. So that's what happens when you go all the way around. That's the pink path, right? Instead of the green path. All right, see from this, if you cancel the R1, the V's, you actually learn 5 minus 300I equals 0. You actually learn that I is 5 over 300 amps. In other words, 1 over 60 amps. See? And then you could go back to your green equation up here and find a meaningful change in potential between VB and VA. So 5 minus 100 times 1/60th. And this gives us, 5 minus 5/3. In other words, it's 10/3. 3.3 repeating. What does that mean? 3.3 repeating volts. So what is the potential difference between A and itself? Nothing. What's the potential difference between A and B? 3.3 volts. You understand? Okay. Now, this is a good question. We took the green path across the top, but what if we had taken the green path along the bottom? You know what I mean? Like, why not, So let's take a look at that scenario real quick. Suppose we had gone all the way around and we'd formed that loop equation at the bottom and learned that I was, like I said, 1/60th of an ampere. Okay? So this calculation is complete here in red. Okay? But imagine we had gone in the green around a different direction. Imagine we'd gone along the bottom. Okay? Along the bottom. And going to the right at that. Let's see what that would look like. So imagine we'd gone this way when we did our partial journey. Well, it would look a little different. You'd have VA and you'd be passing through the resistor. Now you'll notice something though. We're going against the flow of the current. The current's going around this way. We're kind of going the other way. So you would actually add IR2, which is 200I. And then this would equal VB. Notice that was actually a shorter path. It was easier. We didn't have to pass through a battery and a resistor. We had to just pass through one resistor. But listen, you went backwards because you're going the other way around. Instead of going clockwise, you went anti-clockwise. And current, we've already said, is positive following this EMF arrow here. All right, so if you solve for VB minus VA now, you get 200I, and you can insert that I, which is 1/60th, and you probably think, well, I'm just going to get a different answer. Nope. The same answer you had last time, 200 times 1/60th. There's your 3.3 volts again. And notice it's a positive number. It's actually a positive number. Why? Both of them were. It's because B is bigger than A. There's actually a higher potential at B than there is A. How do I know that? Well, VB minus VA is positive, for one thing, right? VB minus VA is positive. Okay, so that was just a little weirder. I typically go around the direction of the loop because then I don't need any weird ideas like going through a resistor as a plus symbol. But, maybe it's so much shorter to go on directly to the right than to go around the long way. Maybe there's like 15 components in the circuit going this way. I'd rather just go the short way in that situation and remember to add IR when I'm going anti-current. All right. Okay. So let's take a look at a real battery situation. If you want to find the potential between A and B in this situation, and this problem's kind of more or less already worked out, you'll notice that I can think of a real battery as really this black box. And inside of it is a little EMF, electromotive force, and a little resistor. So remember, a real battery has internal resistance. Okay, let's say we want to go clockwise. So clockwise is this way around. If you start at point A and go to point B, it's a very short path. It's just this red. So you would say I have potential VA. I pass through the EMF arrow pointing the same direction as the EMF arrow. So you put a plus. Sorry, I was playing around with this earlier and I should have cleaned this up a little for you guys. Sorry. It's plus the EMF arrow because you're going in the same direction. And then minus the IR because you pass through that little resistor inside the battery. And now you're at VB. Done. If you solve this, you get VB minus VA is E minus IR. Right? E minus IR. Okay. Now, if you go around the blue path, you're kind of going in the direction current is not going. In other words, you're opposing the EMF arrow. So just remember to add IR when you hit it. And you can see I have an error here. Let me fix this. I'll just go around again. So you start at the point A, you can write VA. Then you're going along the blue arrow and you hit that resistor and you add IR. And then you keep going and you hit VB. Okay? And so isolating, and I'll write it in blue, VB minus VA is now just simply I big R. All right, I'll highlight it in blue, just like I did last time. All right, so wait a minute. Is VB minus VA E minus IR, or is VB minus VA just I big R? Well, it's both, actually. It's both. So I have a typo down here. If you set these equal to each other, you have E minus IR equals IR, and I wrote that here, and this is the conclusion. E is equal to IR plus IR. So what does that mean? Well, it's actually a fairly obvious statement. It's almost like a restatement of Ohm's law and the two resistors, which appear to be kind of in series in the circuit, combined to make one resistor if you factor out the I. So think of it as almost like the little r and the big R are in parallel, or in series with each other, right? In series, not parallel. They combine to make one resistor called R plus R, and we have one charge pump doing the work. Okay? All right, sometimes we're looking for current, sometimes we're looking for EMF, sometimes we're looking for R, a missing, resistor, whatever. All right. So here are some rules to keep in mind when working with a single loop circuit. And these are some of the rules we'll use also when we get to the multi-loop circuits. First things first, the sum of all the potential changes in a loop is 0. That means if you go from point A all the way around through every component and you keep track of the rises and falls of potential, it rises when you hit a battery and it diminishes when you hit a resistor, you should get the same potential when you end. If you go backwards through a battery, or if a battery is put into the circuit backwards, then of course you include a negative for that, which means you'll, instead of adding a potential increase, it'll diminish. That's actually restated here in bullet 2. The potential change when passing through the EMF is positive when traveling through the direction in the direction of the EMF arrow, but it's negative if you're traveling through in the direction opposite the EMF arrow. Once you've picked your path direction, you can't really change that. You just keep going, plowing through the circuit elements. And if you hit a backwards battery, make sure you subtract that voltage. Here's like rule 2.5. I don't even know if it counts as a rule. When passing through a resistor, use negative IR. Okay, that's it, if going in the direction of the current. So if you are traveling in the direction of the current and you hit a resistor, make sure you subtract IR. If you're going in what you know to be the wrong direction, then just make sure to add IR, of course. Okay. By the way, this 2.5 here, it becomes like a little self-check later. Technically, let's say you're doing a problem and you thought you're supposed to go around one way, and you end up realizing something's wrong, and you end up realizing, hey, that answer doesn't make sense. It could just be that you were wrong all along about the direction of the current. So sometimes it becomes like a little self-check. Okay, 3, what do we do when the current forks? So I'm talking about, actually you've got something like this. Those are batteries, not capacitors. We're going to start using simpler battery symbols. We're going to start using this symbol for batteries instead of this, because we're going to be drawing 3 or 4 batteries, and and they're kind of hard to draw. So don't worry, it's not a capacitor. Capacitor is equal length here. These are equal segments. This one's longer than the other. The positive one's longer than the negative one. So anyway, I was just drawing something and I erased it. Sorry. Imagine you are working with a circuit like this. That's a battery. And then you come over here to another loop over on the right, and you notice something. In that other loop, there's a battery. Okay, this is a true multi-loop circuit. Why? Because there's not really a simple way to redraw it using parallel and, I mean, you could redraw it probably into some topologically equivalent circuit, but this is not just 2 resistors in parallel, you know what I mean? So you can't just use an equivalent resistance rule like 1 over R1 plus 1 over R2 and then reciprocal of that. You can't really combine the resistors because of this darn extra battery. So you just basically keep the loops separate. You assume that the current is on this one is going this way, which means you'll wrap around that direction. And then you're going to do the same thing on this one, but you're going to go around this way. And what happens here is you kind of have multiple currents being produced, you could say. And so what you do when a circuit forks, the sum of the current into the junction is equal to the sum of the current out of the junction. So you kind of have to think of it as water flowing. Let's say the water's going like this in a circle, and then there's water going like this in a circle. Okay? And for the sake of argument, let's say that this yellow resistor is R1 and the green resistor is R2. Okay? So R1 and R2. Sorry, need to pause it. because I want to enlarge this picture. Put a new sheet in here real quick. We'll make it bigger. It's just so you can see it better. All right, so this would be like R1 and R2. What we usually do is we label this I1 because it's the current going into resistor I1, and label this current I2. And usually there's actually a third resistor somewhere, like an I3. I was supposed to put in a third resistor. Sorry. Let me put in one more resistor at the top here. We'll call this R3, and then I3 is the current through that resistor. We usually put, and you'll notice in the book, we usually put our currents labeled right on the resistors, actually. Okay? And because of the way the water is kind of circulating through, it might make sense to just think of, I3 as going to the right. I2 is essentially, when you hit this junction at the top, going to the left because it's coming from over here. And then it passes, both of them pass through and make, a current through resistor 1. So that I1 is really a combination of I2 and I3 coming together like that. So this is the rule we'll use when we hit multi-loop circuits. All right? So that third bullet just says when a circuit forks, and I meant to draw a resistor here. When a circuit forks, the sum of the current into the junction is equal to the sum of the current out of that junction. So I3 and I2 combine to make I1. We'll talk about that in the next video though.